Section 6.2, we're going to continue our discussion of differential equations. Specifically, we're going to look at growth and decay. So this is a category of differential equations that have a very specific form. And they're going to involve a lot of types of things where things grow or decay exponentially. So first of all, I'm going to take a look with you at just where we were before. So this is going to look just like the problems we were just doing, the first one. And then we'll move into something that's a little bit more interesting and has a little bit different dynamic. So on this one, if I move my dx to the other side to start with, this is dy is equal to 6 minus x dx. And I take my antiderivative. So I have y equals what? What's on the right-hand side? Right. What's it going to be? 6x
minus x squared over 2.
And then plus c, right? Okay, so that's where we left off last time. That is one. They're the ones we've done thus far at the very end of section 6.1 and this very first one in section 6.2 are very simple to separate the x's and the y's, right? They're very clear what you need to do. All we had to do is move the dx to the other side. But if you take a look at this next one, it's not quite the same. For starters, it's written as y prime, which is not a real big deal, but it's really been more helpful for it to be written as dy dx, so I will change that notation. And if I shift the dx to the other side, like I've been doing, I have something that I haven't had happen before. What do I have happen right here now? Yeah, I have not separated all my x's and y's, right? So over here on the right-hand side, you might look at this and say, x is being multiplied by 1 plus y. Let's distribute that. That's not helpful. The reason that that's not helpful is because it's very difficult to move the y. So I'm going to show you why it's not helpful, and then I'm going to erase it, and we're going to do what is helpful, okay? So if I were to multiply this out, I would have this, correct? And the problem with trying to move the y right now is that it's added to the x. And not only that, but if you sort of think about it as separation, what I really have here is I have x dx and xy dx. And if I try to move this y now with sort of some, standard algebra techniques, I'd have to subtract it. But then what would happen if I subtracted it to the other side? Now I've moved x's with it. Do you guys see that? This isn't a helpful step. Having it isolated inside those parentheses right up here is actually a better form because notice that the x is currently being multiplied by the 1 plus y. So how could I move the 1 plus y altogether? With division. So I can actually divide by the 1 plus y. And I'm going to write it over here as this multiplication by the reciprocal. So on the left-hand side, the y's are now removed. On the right-hand side, they're now removed. And on the left-hand side, I now have 1 over 1 plus y. And I just have x dx on the right. Now, this introduces another dynamic that I haven't had before. Everything in the 3 problems I've done like this before have simply had dy on the left, correct? So when I put my antiderivative in right here, I'm not just taking the antiderivative of dy on the left anymore. I'm taking the antiderivative of 1 over 1 plus y dy, which means I'm going to have to actually use my antiderivative processes a little bit more fully. So what is the antiderivative of 1 over 1 plus y? It's going to have a natural log of what? Of the absolute value of 1 plus y. Right? Yeah, that's what's going to be on the left. Okay? Keep moving. What about the antiderivative of x dx? X squared over 2. And then we have plus c, right? Okay. Now, in theory, you've done all the calculus work. Not in theory. In reality, you've done all the calculus work of this particular problem, but you haven't answered the question. The question wants us to find the equation y equals, and this is not a form that says y equals yet. I need to change this somehow to say y equals. And those are things we did in chapter 5, and they're actually things that you do in college algebra, depending on how far your class gets as well. It's an algebra technique. Do you remember how we can sort of separate these pieces on the left or shift them around or eliminate the natural? What do we need to do? right? So we want to do the inverse, right? It's always about trying to inverse things. And the inverse of a log function, right, this natural log here, is an exponential. So I'm going to sort of drop in this e, and it's going to become the base, and each of my sides of my equation are going to become my exponents. Are you with me? So on the left, in a very real way, these sort of are canceling each other out in terms of operation status, not like 1 times, 3 times 1/3 is 1. It's not like that, but they do, cancel one another out in terms of their operation. And I'm going to be left with 1 plus y on the left when I do that. That's how I eliminate the logs. Now, the right-hand side's a bit messier, to be honest. I now have e to the x squared over 2 plus c. And our last step, sort of from the perspective of what we've been thinking about, would be then to get y alone. What do we do to do what? You do subtract a 1, right? So this would be y equals e to the x squared over 2 plus c, and then minus 1. Now, this is a little awkward. It's awkward because we don't usually see the plus c written as an exponent, right? Like, that's not where it usually ends up being. It usually ends up being at the end as a plus c. And no, you can't just move it to do that. That's not going to work either. But there is something else that we are going to see, and it's going to happen on all of the problems with growth and decay. And what happens is that we're going to use properties of exponents to rewrite this a little differently. So instead of having this written as a sum in the exponent, we're going to have it be written as 2 separate bases of e. So e to the x squared over 2 and e to the c. Okay, now that may not actually look any better to you, and it probably shouldn't. It doesn't look any better to me, but we're getting there. So what I'd like for you to do right now is to go back, and I would like for you to call all these c's that we've put in C1s. Just change them to C1. I kind of like my answer to just have C in it, and I'm about to change an expression and make it have a C, and it's not going to be the same C value that I had before. So we all recognize that C1, in this case, is a number, right? It's a number. We don't know what it is, but it's a number. And when you take E and you raise it to a number, you get another number, right? Like E squared is a number. It's not a very pretty number. I mean, I like the number, but it's a number, yeah? So this expression right here in red that I've circled, e to the c1, is another number. And in fact, what we're going to do is we're going to rewrite it as that number. So y equals e to the x squared over 2, and the number that I'm going to call this now is c. And what we usually see is that it's written at the beginning, which obviously I didn't need to do in 2 steps, but I wanted you to see where it's coming from. The c is simply a number. So instead of getting a plus c at the end, right, like we've done on so many problems, we end up getting a multiplication factor of c at the beginning. And this is going to happen repeatedly in section 6.2, is that you're going to get this process where you're going to have e to a constant, and you're going to change that to just a different constant. Okay, ready to try another one? All right, this one has a little bit of math language in it that has probably been a minute since you've seen it. So I'd like to remind you of some phrases that you may or may not remember. First phrase that you should remember is rate of change. In fact, I used it in section 6.1. What does rate of change mean? It means derivative. Okay, so rate of change just means derivative. That's fine. The part of the language that you probably haven't seen in a while is this variation language, varies jointly. Depending on what courses you've had and where, it shows up in our college algebra course. And so there's 3 types of variation. There's varies directly. There's varies inversely. And there is varies jointly. And so I'd like to specify for you, remind you what each of those are in the middle of this problem so that we can see a different one of them later. You're going to know what to do with it. So varies directly. So if we say that x varies directly with y, then this means that you could say it either way, but y equals some constant times x. Right? So like this is what happens when you enlarge this. Every time I'm enlarging my screen, it's varying directly. right? So it has the same dimensions as I move it in and out, and it just becomes a larger version of something or a smaller version of something. That's a direct variation. Varies inversely actually ends up looking like that k value is divided by x. So when x gets bigger, y gets smaller. So there's a give and there's a take, right? So like the more time you spend on the phone, the less time you've spent on your homework. It's something like that. That's not exactly a joint variation, but you can see the idea there. Something is increasing as something else is decreasing. That's what inverse variation is. And then, whoops, I'm done underline. And the one that we have is joint variation. Joint variation has 3 values like this. And so you end up with, it doesn't matter which one it is, it's the language that's given, is that you end up with the k value and the other 2 multiplied. So it's a multi-layered direct variation, right? You've got 2 variables on the right, not just one. So taking a look at that and over here at our description, it says the rate of change of y, which we already said was y prime. Actually, let me write it as dy dx because we're going to need to do that later anyway. So the rate of change of y, dy dx, with respect to x, varies jointly as x and L minus y. So varies jointly means it's going to have some constant k, and it's going to have those 2 quantities, namely x and L minus y, that are going to be multiplied. Okay? K and L are numbers. We don't know what they are, but they're just numbers. There's still only 2 variables here. X and Y are our only variables, okay? But K and L are acting as numbers. So just like with the other problems, I want to move all of the X to the right, and I want to move all of the Y to the left. So my first step, moving the dx over there, is fine. But after that, I need to still move the Y part, right? That L minus Y, it's got to go over there, and it's going to act much like the last one did, right? It's going to come over here as a fraction, 1 over L minus Y dy, and it's going to equal kx dx. And we're going to take our antiderivative. Let's do the right-hand side. It's easier. What's the antiderivative of kx? Antiderivative, not derivative, kx squared over 2, right? And then plus my c, good grief, plus c. On the left-hand side, I am going to get a natural log, right, just like I did on the one before. But over here, there really was a u substitution. It just wasn't very exciting. I mean, 1 plus y as the interior of a u substitution, because its derivative is just 1, doesn't help us or doesn't change anything. Here, I do need a u substitution. You may or may not need to see it written. I'll write it down just in case. So the u here is actually L minus y. What would du be? -1 dy. So I'm going to end up with a negative on this one that I didn't have to deal with before. So this will be a negative natural log of the absolute value of L minus y. There will be a negative present because the derivative of the denominator, right, the L minus y is actually a -1. Goal is to solve for y. What would I do first? Before. I got to get the negative out of there first, and then I'm going to do the e. Yep. So we're going to do the negative first. So this is negative kx squared over 2 plus, and these are going to be called C1, so we're going to change them later, so I'll call them C right now. And then we're going to do the e, just like Connor said. So here's my e. So on the left-hand side, this is now going to just be L minus y. On the right-hand side, I'm going to have e to the negative kx squared over 2, which is kind of ugly, and plus C1, right? But I can rewrite that as 2 pieces like this to the C1, and then I can make that a constant in front, c e to the negative kx squared over 2, L minus y. Okay, I'm making progress. I'm almost there. What's next? Subtract the L. So we have negative y equals c e to the negative kx squared over 2 minus L. And then what?
Divide the negative over.
Yeah, we're going to multiply by or divide either way by a negative. Yeah, so this will end up being y equals negative CE to the negative kx squared over 2 plus L. And the k and the L could be, any numbers given and worked the same way. All right, I feel like we should do one that doesn't have logs in it. Yeah, good. This one won't. This one does have an additional direction, though, that the other ones didn't have. What do the directions say here that's going to be a little different? You have a point given. What's that mean we're going to be able to do?
Find a particular solution.
We're going to find a particular solution. We're going to find C on this particular problem. Okay, we're going to be able to find C. The problem starts out the same way. This one has t's and y's in it, but dy is equal to negative 3/4, and I'll write it as t to the 1/2 dt. We'll find our antiderivative. It's cleaner than the last two have been. I just have y on the left. What do we get on the right? I'll start. It's negative 3/4. Now what? T to the 3/2 times 2/3. And we need the plus c, right? All right, we'll clean it up. Y equals, let's see, those 3's cancel. I've got a negative 1/2 here. Negative 1/2, the square root of t cubed plus c. Then what? If I were finding a general one, I'd be done, right? So what do I have to do now that I have a point given? Plug it in for the x and the t. So the t value is listed first. It's 0. And the y value is a 10. So this is 10 equals negative 1/2 square root of 0 cubed plus c. What is c? It's 10. And our solution then, where was it? It's right here, would be y equals negative 1/2. Either you've got the square root of t cubed plus 10, or you could see this written as t square root t. Right? That's a possibility. I don't care if you see that or not, but I'm just wanting to know if you see something that looks like that, don't just assume you did something wrong. Pause for a moment and consider some properties. These are the same thing. Okay? All right. Let's do the setup for this one, and then I will pause, go back to my office, finish recording, and then you guys can watch the last bit. It looks like there's still a lot to do, but the questions that are left are very quick, okay? The rate of change of y, this is one where it starts out with language pieces that we have to change as well. The rate of change of y, that's dy dx, is proportional to. This phrase, proportional to, is the same thing as saying direct variation. Okay, it's one of the phrases that means the same thing. So it's going to have direct variation, so it's going to have k to y. So direct variation are proportional to y. It gives us some information. It says when x is equal to 0, y is equal to 6. When x is equal to 4, y is equal to 15. What is the value of y when x is equal to 8? It gives us a lot of pieces of information. But the first part of it that it doesn't actually say, but we have to do in order to actually use that pieces of information to finish the problem, is that I have to do all the differential equation stuff that I've been doing. Okay? So I've got to shift things around. I've got to take antiderivatives and so forth. So this is dy is equal to ky dx. What's next? Divide by the y. So this is 1 over y dy is equal to k dx. And I'll take my antiderivatives. So I have the natural log of the absolute value of y is equal to kx plus c1. Let's get to our differential equation and we'll stop. We put our e as our base, right? And this y would become e to the kx plus c1, which is the same as e to the c1 which is, we've done it now 3 times, or this is time number 3 anyway. So my differential equation solution, the general solution, is y equals CE to the kx. Is everybody good with that? Okay, I'm going to pause right there. I'm going to finish up the recording for it so that you can see how that finishes out. And then the last bit is related to how it affects exponential growth and exponential decay. All right, so we're at the point where we actually have 2 variables, right, C and K, and we're trying to find both of those variables to find our particular solution. But we're given a lot of information. We're told when x is equal to 0, y is 6, and when x is equal to 4, y is 15. The question at the end, what is the value of x when y when x is equal to 8? We need to answer that, but we can't answer that until we have the equation to answer it from. So that part's secondary. Now, technically, we could use either piece of information, x equals 0, y equals 6, x equals 4, y is equal to 15. But the one that's most easy to use is one that's going to have a 0 in it. So that's the one we're going to start with. So we're going to let x equal 0 and y equals 6. So 6, and this is CE to the k times 0. So as we did before, right, e to the k, or k times 0 is 0, and then e to the 0 is 1. So this will tell us then that C is equal to 1, okay? Sorry, 6. C is equal to 6. So that's helpful because that actually gives us one more layer of things we know up here. So now I have y equals 6e to the kx. And I can use that equation to plug in the last piece of information, this one right here. So when x is 4, y is 15. So here's y is 15, and here's x is 4. So k times 4. Now, our goal is to solve for k, and it's going to be ugly, right? Like it just is. We're going to simplify this. This is dividing by 6 would be 15 divided by 6, e to the 4k, right? And then in order to get the 4k out of the exponent, we're actually going to take a log of both sides. This is the natural log of 15 over 6 equals, and you could reduce the 15 over 6 if you want, equals 4k. And then our last thing to do is to divide by our 4. So we're going to take and approximate the k value. We're going to use 4 decimals is usually sufficient. If you want to use more, feel free to do so, but 4 is usually sufficient. It might tell you to use 3 or 5 or something too, so just pay attention to that. But the approximation that we would get here is actually 0.2291. So that's my k value. So what that means is that my equation is y equals c is 6, and then we have e to the k, which is 0.2291x. Right, so this is my particular solution. But I want to use that particular solution to find the value for y when x is equal to 8. So I'm going to take the number 8, and I'm going to put that number in for x. So 0.2291 times 8. And if we put this in, we'll generally, again, round our answers to 2 decimals. So why are we doing 4 in the middle and 2 at the end? Because we want it to be accurate to 2 at the end. And if we round too quickly in the middle, it will not be accurate to 2 at the end. So if I round this off, my answer ends up giving me, I should put approximately, just so you know. This is an approximation, of course. It's 37.51. Okay, the last part that we have in this lesson is actually talking about what growth and decay are in terms of what we've been working with. And so number 5, this one we just did, is actually an example of a growth model. And the reason it's a growth model is because this value that we found for k is greater than 0. If the value is positive, we actually have a growth model. If the value is negative, we have a decay model. And this is actually what we've got as our definition, some of those pieces. So if y is differentiable function of t, and y is positive, and y prime is equal to kx, right? That's how we started this with, right? Y prime is equal to kx. That's one of our very first thing we wrote down on example 5. Then y is going to equal c e to the kt. Notice that's exactly what we got right here. I'll circle it. Y is equal to c e to the kt. That will always happen. We call k the constant of proportionality. Oh, I skipped over it. We call c the initial value. We call k the constant of proportionality. And if k is positive, it's growth. That's the problem we just had. If k is negative, it's decay. And it's either growing or decaying exponentially. These are exponential functions. So what we're going to be doing with this is very algebra-like. We're going to do an example. This is the last one we have. And this is an example of half-life. So this is a half-life example of radium-226. So you may or may not know much about what this is, but this is the idea that the point when half of this object of 20 grams of this radium remains is after almost 1,600 years, right? It takes 1,600 years for half of it to go away. And so this is used in carbon dating. It's used in trying to figure out the age of certain fossils and things like that when scientists are digging, those kinds of things. That's an exponential decay model. A similar exponential growth model actually occurs when we look at the growing of investments with money. So we have exponential growth in that particular example. You also have probably heard of things before like rabbits multiplying exponentially. That's an exponential growth kind of model that they're following is what there's referencing. So, all right, so this one is actually telling us that we have a half-life of 1,599 years, and we have 20 grams now. So exponential growth and decay always follow the model that we were given on the previous slide, which is y equals c e to the kt. And we use the information right here about the half-life, right, half-life, to actually figure out what K is. So it tells us that we start with 20 grams. That's sort of irrelevant, but we'll see why in a minute. And if it's half-life, we want to know when half of it remains. Well, half of it is 10. And then we're going to find e to the kt, and the t value, is the years that we were given for the half-life, which is 1,599. Notice the very first thing we have to do is to eliminate the 20 that's in front, and it'll always become a 1/2 and a half-life problem. Okay, there's other ways to find, like more formulaic kind of ways to find half-life. I'm not interested in that you do that. I really would like for you to show this from the perspective of the exponential growth models that we're working with. So this is 1599K. And we'll do what we did on the last problem, which is we'll take the natural log of both sides. So I now have the natural log of 1/2. And natural log and e's are inverse operations, so that leaves me with the 1,599K. We'll divide by 1,599. And when you put this in your calculator for an approximation, it's going to turn it into scientific notation. So just pay careful attention to that. I'll use 2 decimals here because with scientific notation that it gives me, this is going to actually be, I'm going to write it in parentheses, times 10 to the negative 4th. So I actually have a lot more more decimals than just 4 decimals here already. So I'm just going to write 2 of them down. So this K value is approximately negative 4.33 times 10 to the negative 4th, which means my model is y equals 20 e to the negative 4.33 times 10 to the negative 4th times time. And if I want to figure out how much of this substance will remain after 1,000 years, I'm going to put the number 1,000 in for x. So this is 20e to the negative 4.33 times 10 to the negative 4th, and I'm putting in the number 1,000. Now, think about this. The half-life is 1,599. So it's not going to dwindle to more than a half, right? Like I will have more than 10 grams when I'm done. 10 grams would be half of it. It's going to take almost 1,600 years before I have half remaining. So I'm going to have more than half remaining. And if we put this in and we round to 2 decimal places, we will get 12.97. And it is in grams because my original quantity, 20, was given in grams. So this is 12.97 grams. So this is what happens when they're trying to determine, like how long it takes before a radioactive site is inhabitable, right? Stuff like that is how does this decay work? All right, we have one more example. It's the same kind of question. It's just asking us what happens in 10,000 years. So we're doing the same thing, but we're putting in the number 10,000. Now, the number 10,000 is much bigger than the number 1,000. And it's also much bigger than the half-life. So we're going to expect that this is going to have decayed a lot more down than just 10 grams remaining. So I have negative 4.33 times 10 to the negative 4th. And I've got 10,000 years now instead of 1,000 years. If you let your calculator do all that, it will actually give you that it's 0.26 grams. Do be careful with all of the exponent stuff going on that you make sure that you multiply all those exponents together before you take that e to that power. So just be careful if you're concerned about your parentheses or that your calculator might not be doing it right or getting answers that don't make sense. It probably isn't then. And you might just want to simply multiply these exponent pieces together first and get that result, keep 4 or 5 decimals and raise that e to that power and then multiply by 20 to make sure that you're getting the right value.